All right. Okay, so now that we're being recorded, any questions about previous lecture or homework or anything else? Okay. In the chat, if you would, if you feel that there is such a thing, if there's any topic that we've covered so far that you have found confusing or especially difficult, you can just type the general topic or theme into the chat window. Meanwhile, I'm going to give you your first quiz or poll of the day. All right, I want to be able to provide resources to you that make a difference. Now, I've done that over the years in a different format when we've been able to meet face-to-face and have lectures and face-to-face office hours and that sort of thing. I want to make sure that I'm doing the right thing when we do this via Zoom and when we're making more use of D2L. So I'm going to give you some options here. I sure hope I checked the right box. I did. That allows you to specify more than one answer. I'm going to just confirm that that's the case. Bear with me for a moment. All right, it's certainly true now. So take a moment to complete that poll. I'm giving you some options over how you would like to have, if you would, additional exercises or checkpoints to test your understanding other than homework. And I can do this in a couple of ways. I can do no credit, no grade in-class exercises where I pose you some questions, I give you a few minutes to work on it, we come back, we talk about it, okay? I can do in-class exercises, quizzes for credit. So I basically take a pause, you go to D2L and you complete a quiz in D2L that does that. I can do the same thing, but make those D2L quizzes happen outside of class time. And I can also have some for credit quizzes as well. Again, my main focus is here is not to use these as assessment instruments, as they say. In other words, I believe I have other ways through homework and exams primarily, maybe an occasional quiz to assess you. I'm trying to find ways that help you to reinforce the knowledge, and research suggests that being asked questions, quizzed, tested immediately after learning helps to reinforce it, but it's also a way for you to just check that you really understand the kinds of things I'm expecting you to. So enough talking for me, I'll take a look at these. Almost everyone's responded, about 5 people have not. Okay, I'm going to close the poll and then I'll share the results with you. So it looks like 80% nearly would like extra credit outside class quizzes. Maybe the homework has convinced you you need lots of extra credit. And 60% would like no credit, no grade in-class exercises. And about 45 are fine with extra credit in-class exercises and quizzes. All right, this is very, very helpful. And I will, I'll do a mix of these. Absolutely. Can there be 2 or more attempts for quizzes? And then people are having issues with nested interrupts and interlocking signals. Okay. I may try to dedicate some time at the end of today's lecture. Yeah, exactly, Mel. All right, that's very useful. So let's get started. I'll try and cover those review topics a little bit later. I'm going to get through some of the material today. I did share the results, did I not? Okay. All right, can everyone see the slide okay? Great. All right, so today's topic is memory basics. We're going to be covering memory quite extensively in this class. And that's because it plays a huge role in microprocessor systems and systems design, and a very, very large role in performance. So today is only one of three, and I'm not sure we'll get through all of it today even, 3 modules that I've created around memory, and we'll cover the basics in memory during today's lecture. And we've already lost sync apparently. Doesn't appear that the slides are advancing. Oh, there we go. Anybody know what that is in the bottom right?
That's a memory cell.
Not a memory cell, but that is actually what is called core memory. That was one of the earliest memory technologies. Those are actually little ferrite cores on wires, and the actual magnetic flux on those cores was detected. So not a very dense memory, but that was a memory technology actually used throughout as late as the early to mid 1970s until semiconductor-based memory began to be used. So the topics we'll cover today, I'll give you a little bit of a taxonomy of memories. Does anybody know what a taxonomy means or what a taxonomy is? If you know, feel free to unmute and give me your definition.
A classification?
Yeah, it's a classification, thanks. Some of you may be familiar with the Linnaeus taxonomy, the fellow who first came up with the idea of things like kingdom, phylum, class, genus, species, etc. It's a way of categorizing or describing things. I'll take a look at the memory hierarchy, and this is a very, very important concept. In fact, the memory hierarchy is where we'll spend probably a third to a half of the course content when you consider that caches and disk drives are part of the memory hierarchy as well. Hopefully today we'll get through register files and some basics of SRAM, SRAM memory cells and devices, and we'll talk about memory organization and the concepts of latency and bandwidth, which you got exposed to a little bit in reading the Patterson paper before. And we'll introduce the concept of interleaving, and if time permits, we may even get to some basics of DRAMs today. So, a memory taxonomy. The unfortunate thing about memory terminology is that history has left us with some things that are misleading or inaccurate. For example, you all know that ROM, R-O-M, stands for read-only memory. And you also know that RAM stands for random access memory. Does that mean that a ROM is not random access? No, a ROM is also a random access memory. So it's kind of misleading that we've chosen these terms early on. So I'm going to look at sort of 3 basic ways to categorize our taxonomy here. In the first, we can describe whether or not something is capable of read and write or read only. We can also describe whether something is volatile or not volatile. I assume that read-write versus read-only is pretty self-explanatory. In read-only, we are only able to do reads from the memory. And the question, of course, arises is, where does the memory get its initial contents? And we'll talk about that in a minute. For volatile versus non-volatile, that simply means, does the memory retain its contents when power is removed and then reapplied? So for non-volatile memories, if we remove power and we reapply power, the memory retains its contents. For volatile memories, if we remove power and reapply it, the memory contents are lost. Another dimension is non-random access versus random access. Let's take a look at the random access category first. You'll find in there, of course, SRAM, ROM, PROM, and DRAM. So they're all random access, okay? It just so happens that ROM is both random access and read-only. Um, Random access initially meant that we could randomly access any element of memory and that it took the same amount of time. In other words, it didn't take longer to access one piece of memory than another address in memory. Technically, even in random access memory these days, that's not really quite true, as you'll learn in the next lecture or so. A better way to think of it might be that I don't have to go through other references or accesses to get what I want. If you think about a tape drive, for example, clearly if I want to access something that's farther down the tape, I need to read through the tape to get to that point on the tape. So it's not truly random access. As I said, these days, technically DRAM really isn't truly random access, but for our purposes, everybody would call it that. There are a few types of memory other than things like tape drives that are very, very specifically non-random access. An example would be a shift register. If I have a shift register and I want to know the value of this bit, the only way to get to that bit, once my zoom catches up, would be to shift that shift register n times if there are n bits to the right of it. Okay. A FIFO would be another example. In order to access something inside a first in, first out buffer, I would need to extract or pull things out of the head of the buffer until the item I want rises to the front of the FIFO buffer. Less familiar perhaps to some of you are content addressable memories. These are memories that, believe it or not, you address by their contents rather than their address. And these are commonly used in networking applications. They can be used to store, for example, network IP addresses and so on. So we can use these for routing tables and that kind of thing. These three items, although they're not uncommon, they're not going to be what we spend our time on in this course. We're going to focus mostly in the SRAM and the DRAM, and later we'll talk a bit about flash as well. Now, in terms of where read-only memories are programmed, in the case of PROM, a PROM means programmable read-only memory. So there typically is either a mode for the device, or we put the device in a separate thing called a programmer, a piece of hardware that we can use to, in essence, program that read-only memory. And then once we have programmed it, remember it's non-volatile, so we can remove it from the socket in this hardware programmer and then place it onto a board or whatever, and then it's retained the memory contents. A mask ROM, those of you who are gamers from quite some time ago, the early game cartridges distributed the game program, the game code, on essentially cartridges that were, bear with me here, I'm not sure why we're having this problem. Those game cartridges were essentially mask ROMs. And in the case of mask ROMs, the bits that are stored in the ROM are determined at manufacturing time. So one of the last layers, if you will, of the masks that are used to produce chips could be used to program the contents of the mask ROM. All the other logic and stuff like that would be fixed for all of the mask ROMs. But the mask layer for the bit contents could be customized for each mask ROM. You're familiar probably with DRAM, of course, and double data rate DRAM. You may or may not know about GDDR and LPDDR. GDDR is graphics double data rate DRAM, a somewhat specialized application, and LPDDR is low power DDR, sometimes used in automotive applications and embedded systems. So that's a brief review, I hope, of memory taxonomy. Memory hierarchy is an extremely important concept in microprocessor system design. What we're doing in memory hierarchy is we're thinking about memory from the very lowest level and closest to the processor to the farthest from the processor out here. Now, obviously, if you remember anything about microprocessors, you know that we have a control portion and we have the data path. And we kind of reviewed that a bit when we talked about basic IO and the x86 architecture. A part of the data path is what are the registers. Sometimes we call this the register file, by which we just mean that there's a bank or a set of registers with IDs, like register 0 through 15 or register 0 through 31, for example. But these registers are an integral part of the processor data path. They are part of the data path. And one of the things I'll do is I talk about each level in this memory hierarchy is not only where it is, but what it's used for. And later we'll even talk about how it's managed. So what are registers used for? What is stored in registers?
Operands?
Operands, exactly right. Only in very strange computer architectures, well, I shouldn't say strange, unusual, do we ever store instructions in registers. So we're storing the operands in registers. So if we want to operate on something, do an add, do logic operations, etc., those are where intermediate results. We could have addresses in registers. For example, load and store are going to use one of the registers for the address of the operand in memory. Okay, but they're for intermediate results, essentially operands or addresses of operands. Now, we typically these days have at least one on-chip cache, and we may have a second level on-chip cache. We could even have a third level on-chip cache, or there could be a third level off-chip cache. It's even possible to have a fourth level cache as well. Now, let's just assume, because I drew it this way, that we have two caches on chip, a first level cache, sometimes called L1, and a second level cache called L2. Now, what kind of stuff is kept in our L1 cache? Well, it could be instructions or operands. Basically, the L1 cache is simply caching whatever is in DRAM. And what does a modern computer architecture put in DRAM? Both program and data, right? So our L1 cache is caching a subset of the DRAM contents. So it's going to contain instructions or data. In fact, we'll talk later about separate L1 caches that are dedicated to either instructions or data, or integrated L1 caches where the instructions and data live together in the same level 1 cache. L2 cache is, again, just another level of cache. And then the third level or fourth level could be off chip. Now, finally, we get, I shouldn't say finally, we get to main memory, which in most systems these days is DRAM based. I should mention that most caches are SRAM based. So main memory is DRAM. What's there? Well, obviously instructions and data. And believe it or not, DRAM is also used just as caches cache DRAM contents. DRAMs can cache files or subsets of files. If the operating system is repeatedly reading a file or a part of a file, then the operating system may cache most recently read blocks from that file in DRAM, so that when we go to do a read operation again, we don't have to go to disk, which, as we'll see in the memory hierarchy, is very, very slow compared to DRAM accesses. So don't forget that DRAM can contain cached blocks of files. Now we get to secondary storage, which could be disk or what? Could be a solid state drive, right? And what's in secondary storage? Well, our file system is typically there, right? That's the main use of secondary storage. It can also be used for paging, and we'll talk about virtual memory and paging later in the course. So when we can't fit everything we want into DRAM and we have to page things out, they would be paged to a portion of the disk that's dedicated for pages from DRAM memory. We can also have tertiary storage, which is typically either tape, magnetic tape, or optical disk. And tertiary storage is used either for archive or backup. So, we archive something so we can free up disk space, or we do regular backups. So if we have, for example, a disk-based system, we may do backup to optical disk or another magnetic disk, or sometimes even still today, some types of tape cartridges. So this gives you a sense of the sort of levels in the memory hierarchy. I could have just as easily drawn it as a pyramid, if you will. The main thing to realize is that we move away from the processor. A couple of characteristics are nearly always true. As we move away from the processor, we are seeing increasing size of that level in the hierarchy. How many registers are there in a typical microprocessor these days? On the order of about, what, 16 or 32, right? Contrast that with how many locations there are in an on-chip level 1 cache, right? Hundreds of thousands, maybe even millions. Even larger second and third level caches. How big would we see main memory systems be? On the order of gigabytes.
16 gigs.
Yeah, easily. And then our secondary storage, our disk drives these days would be what? 2-4 terabytes or more, as you saw in the homework exercise. And then optical disk jukeboxes and so on, and tape storage, even larger. So as we get further from the processor, we get increasing size. We also, however, get decreasing speed. For example, our registers need to be fast enough to do what? Operate at the same speed as the processor. It wouldn't make much sense if our processor was extremely fast, but it took 4 or 8 clock cycles to read a register, right? Because every instruction essentially operates on a register. It would make no sense to have registers that were not capable of operating at the same speed as the processor. Obviously, the reason why we have caches is that they are what? Faster than DRAM, right? And of course, DRAM is hundreds of thousands, millions of times faster than disk storage. And tertiary storage could be really problematic. It could take minutes to access a part of a tape, and it could take hours to use a robotic arm to retrieve optical storage or something like that, or tertiary storage that is no longer stored online. The other salient feature is the farther we get from the processor, the more that the cost per gigabyte drops. So obviously tertiary storage is really, really cheap, as you saw in the case of the Patterson paper. Registers are quote unquote expensive because they're part of the die for the chip, right? The more registers we have, and we'll talk about why that's a problem, they not only take up more space, but also the more registers you have, you need to dedicate more bits in the instruction words so you can address those registers. So what might a memory hierarchy look like for a quote unquote typical system? Well, it depends on the nature of the system. If you're looking at a personal mobile device, like a smartphone, for example, even smartphones typically have at least 2 levels of cache. So we'll have an L1 and an L2 cache. The CPU, fairly standard. We might have on the order of 1K bytes. That's because we might have, say, 32 registers, but those registers themselves might be what? They might be 64-bit, right? Or even larger on some processors. So that's an 8-byte register times 32, right? So that's the ballpark. And then our L1 cache, oh, and I should mention the speed needs to run at the speed of the processor. So maybe roughly 300 picoseconds for a typical processor that's used in a mobile device. L1 cache, and again, these are just orders of magnitude, 64 kbytes, and with about a 1 nanosecond access time. An L2 cache, a little bit slower, 5 to 10 nanosecond access time, but larger, about 256 kbytes, more or less. Main memory on a mobile device might be in the 1 to 2, maybe a little bit bigger these days, gigabytes. And access time for a DRAM-based main memory might be in 50 to 100 nanosecond range. And then the sometimes we call this, by the way, persistent storage, meaning it stays around. When you do a reset or whatever, what happens to DRAM? First off, you power off, DRAM is volatile, right? So contents go away. But where are your apps stored? Where's the operating system stored on your smartphone? In persistent storage. And that's typically in flash memory. And sizes of these will vary, but it's on the order of about 4 to 64 gigabytes. And notice the access times now, 25 to 50 microseconds. Okay, now for a laptop or a desktop machine, we're typically going to see probably 3 levels of cache. We'll see much, much larger last level caches. We will see typically larger DRAM sizes, and our persistent storage, in this case, assuming flash again, might be in the 1 to 2 terabyte range. I think the last laptop I bought was a 2 terabyte SSD, and that was a couple of years ago. In a server, we're going to see possibly even L4 caches, by the way, especially in the PowerPC based servers. We're going to see fairly large DRAM sizes, and we'll probably see a combination of hard disk drives, sometimes called disk storage, HDD, and solid state drives, SSD. And not unusual to see, this isn't a single drive here, by the way, but 64 terabytes might be several drives that a particular slot in the server has. So this is the memory hierarchy, okay? As we get farther from the CPU, we get larger memories, they get slower, and they get cheaper per bit or per byte. That's the main thing to take away. And of course, remember what the function of each of these levels in the hierarchy is. What's stored there, and what's its purpose? How does it get there? So let's start now at the, if you will, I guess, the tip of the hierarchy. Let's start with register files. Now, register files are used for the general purpose registers on microprocessors. They support the CPU architecture's data paths. So if you have an instruction like add R1, R2, R3, if the RTL semantics of that would be, that's equivalent to R1 gets the contents of R2 plus the contents of R3. This would be an RTL description of the semantics of that particular instruction. Well, then the register file needs a way to select 3 different operands, right? Because we have 3 operands involved in that operation. We've got 2 source operands, so we're going to read those, and we've got 1 destination operand, so we're going to write that. So we need the ability to provide 3 different addresses to the register file. 1 for this operand, 1 for this operand, and 1 for the operand that we're going to write. And we need to obviously be able to provide data in and data out. So if our registers are 32 bits, then N here is 32. Okay, so we have a 32-bit write and 32-bit read, okay? Now, how do you build a register file? Well, conceptually, and actually fairly close to how it would actually be done in technology, you can think of a register file as basically just a 2-dimensional array of flip-flops that have tri-state or tri-statable outputs. So what you see vertically here, these lines labeled B0, B1, B2, and B3, etc., these are called bit lines. And the bit lines, as the name suggests, carry the values of the bits for that bit position. So in this simple example here, I'm assuming I've got, just hypothetically, 4-bit registers, and I've only got, say, 2 of them shown anyway. So I've got 2 4-bit registers. So each register is comprised of 4 flip-flops. So let's call this register 0. There's a flip-flop, there's a flip-flop, there's a flip-flop, and there's a flip-flop. And they share a common output enable signal. If their output is not enabled, what do? They tri-state their output. So you see a little tri-statable driver at the end of every flip-flop. Okay, so only if they are selected, so in this case, if select underscore reg 0 is true, will their driver allow the value of that flip-flop to drive what? The corresponding bit line. If their output enable, their select bit here, is false, then they will not drive the bit line. They will tri-state it. Okay, so any register 0, 1, 2, 3, etc. that is not addressed, does not have a select reg signal true, will tri-state its outputs. This is important because what's connected to those same bit lines? The outputs of each of the bits for register 1. And if we have more registers, reg 2, 3, etc. So only one of these select lines will be true at a time. In fact, at most one. And it's that one that will then enable its address to drive its bit values onto the bit lines. Okay, those are shared bit lines. So we have to have tri-statable outputs when we're driving a shared signal in this case. Okay. Now, oftentimes we need multi-port, as I said. So we need not just one data out, we might need two data outs. We want to be able to read R2 and R3 concurrently. Otherwise, our processor would be slower, right? We'd have to read one register and then the next clock cycle, read another register. We'd like to do both of those reads at the same time. You might say, well, wait a minute, but why do I have to be able to do a write at the same time? Because don't I do it later? Don't I do the addition first and then do a write? Yes, you do, but it's a pipeline processor. So what's happening when we are doing our read of R2 and R3? An instruction ahead of us in the pipeline, maybe that occurred up here, is writing its destination register. So even though we don't write our destination register in the same clock cycle, we write it a few clocks later after we've done the add, for example, some other instruction that preceded us in the pipeline is doing its write at the same time. So we need to actually have three ports. We need to have an A port for reading, for writing rather, and then a B and a C port for reading at the same time. And we'll get later to how we go about implementing that. Now, what about writes? Well, we only talked about reads. For writes, we have to add a little bit of circuitry to the basic cell, and we have to make the bit lines bidirectional. So let's look at the control circuitry first. We want to generate a signal for reading the selected line. Here we just had to select the line. And we want to generate a signal for each word or each register for writing that selected line or word. And of course, this bit cell will be replicated for each bit in that register. And it's replicated up and down for each word in the register, for each unique register rather. So we'll have a global write enable that says that we're doing a write or a read, and then we've got our select signal. Are we selecting 0, 1, 2, 3, 4, etc.? So if we're selecting I, okay, and we're doing a write, then we will do write select. And if we're selecting I and we're not doing a write, then we select read select. Now we already know how read select works. It's just going to do what? It's going to control the driver on that tri-statable buffer and allow it to drive this bit line. Okay, and then the next cell would drive its bit line and so on for bits, say 3 through 0. But notice we've got a little feedback path now. We take the output of the flip-flop and we feed it back through a multiplexer. The other input to that multiplexer comes from the bit line itself. So that suggests that if we want to do a write operation, we need to do what? We need to place the value that we want to write on the register onto the bit line. We're going to drive the bit line rather than read from the bit line because we're doing a write operation. So we place the value, a 1 or a 0, on the bit line for each separate bit line, bits 0, 1, 2, and 3. And then if we've selected write enable and this register, then that will make the multiplexer choose what for its input. It'll choose the 1 input, which is this bit line, and it will drive it into the flip-flop. In other words, we're now setting the flip-flop with the value that's on the bit line. If we're not doing a write, if we're doing a read or we're not doing anything at all, what happens to that flip-flop? Its value goes into the 0 port, and this write select line will be 0, and we'll just keep circulating the same bit into the register file. Okay, so this is how we build read-write register files. Now, we kind of finesse something, which is that we talked about these select lines here, 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 etc. But we don't really do that, do we? Because that would mean that if we had a register file with 64 registers, we would need what? We'd need 64 signals for each port, right? Those are essentially one hot encoded, right? I raise one of these values, all the others are 0. And we don't address registers or memory that way, do we? We use binary encoding, right? So if I have 2 to the n registers, I only need n address bits to address them. I don't need 2 to the n bits. So what happens, of course, in front of, I'll say this later too, in front of every memory is a decoder. So that way we provide an address. In this case, I call it reg ID rather than reg select. I provide an n-bit address, and out of that, I get a one-hot encoding that is 2 to the n. So exactly one of these outputs will be a 1. So for example, if I have a microprocessor with 32 registers, how many bits do I need to specify which register is involved as an operand?
5.
5, right? So I have a 5-bit address, and then one of 32 of these select lines becomes high to drive the appropriate row in the register file. And you can see what a simple decoder would look like here. I've got 3 address bits, and then this is a decoder implemented here, and then I get 8 or 2 to the 3 select bits coming out of it. So again, in almost every case, very few exceptions, the very first thing that happens in a memory is a decoder, right? We take n bits of address and we need to generate essentially a way to access 2 to the n different things. So what does a, we all still here?
Yep.
Okay, for some reason my Zoom did some strange things here. Okay, now, how do we actually access a register? What does the timing look like? Well, read operations are pretty easy. They're sometimes called address following. And by this, I mean simply that, look, if you want to read from a different location from a register file, or in some cases, many kinds of memory, not DRAM, all you do is change the address. It just follows the address. So in other words, if I have a register file and I change the register ID value from 3 to 7, then what will I see on the output? Instead of seeing the contents of register 3, after a while, I'll see the contents of register 7, right? So here's my register ID. In this case, X is 3. And what do I see on the output? The contents of register number X. I change the register ID to 7 or Y. What happens? Some amount of time later, I see the output be the contents of register Y, or 7 in this case. Okay, that's all we mean by address following. You change the address, and some amount of time later, after some delay internal to the device, you see the output for the newly selected address that you're using. By contrast, writes are typically synchronous, which means to say they're synchronized to a clock. And we also need an additional signal, write enable, to indicate that we're doing a write. Now remember, write enables are just as often active low and might look like this instead, right? Now, when we're doing a write, we're going to do 2 things differently. One, we obviously have to provide the value we want to write. So in this case, it's data in. So we don't provide any value, don't provide any value, maybe it's even tri-stated. And then we apply the value of the data we want to write, and we provide the register address, and then we make write enable be true, and in this case, true means high, in this case, true means low, and then we wait for the clock, and then the clock happens, and voila, we write the register file. Now there may be some rules that say, okay, after the clock, you have to continue to hold that value for some amount of time after the clock edge, and that you may in fact have to continue to assert write enable for some time after that clock edge. All right, and there may be some rules that say you have to provide the value and the address for some amount of time before that clock edge. Remember, those are called what? Hold times and setup times. Okay, but the basic principle is the same. Okay. And we'll talk soon about how we do multi-ported register files. Okay, so that's the basic way in which we implement the first level of the memory hierarchy. How do we build register files on the processor chip itself as part of the data path? The next type of technology, which by the way doesn't occur only in caches. You can buy individual SRAM chips today, and these are static RAM. Okay, SRAM or static RAM. By the way, static does not mean non-volatile. Okay, if you turn the power off and back on again to an SRAM, you lose the content. So static doesn't mean non-volatile. Its meaning will become clearer in just a moment. The basic idea of a word line, that is a line that is selecting which group of bits that make up a word, so they're going to drive their output to the bit line. And the basic idea of bit lines is relatively unchanged from register files. Okay, what's different is how is the memory cell itself made. So rather than being kind of like a flip-flop, we think of it more as like back-to-back inverters. So in other words, we've got a bit in there and that bit just keeps circulating around. Okay, the address is much like the unary encoded one-hot register select line, right? It serves as a word line or a word select. And then we've got, in this case, both a bit line and the complement of the bit line. In SRAM technology, we're typically using 6 transistors, 4 for the back-to-back inverters and a pass transistor each for reading or writing the bit line. Now, how do reads work? Well, reads basically you select the desired word line. So we apply a 1 on the address line for the word we want to read. Remember, before this, though, we have a decoder, so we don't have to have 2 to the n bits. We only have to have n bits into the decoder, and then we get 2 to the n outputs, and they select each of the word lines. So we select a word line, and then 1 bit line is going to get pulled up, and 1 bit line will get pulled low, depending upon whether we've got a 1 or a 0 there. Okay. In the case of a write, we're going to write the bit and its complement onto the bit lines, and then select the row, which will then essentially turn on the pass transistors, and we'll write the bit into one side and the bit's complement into the other side, and then they'll essentially circulate like that. Now, a couple of important points to point out. One, what will be longer, bit lines or word lines? Well, we'll typically have many more words than there will be bits per word, right? In an SRAM, we might have, let's just say, for example, we can have 256K locations in our SRAM, right? And yet, how wide would it be? Maybe only 8 or 16 or 32 bits wide, right? So we won't have a great large number of bit lines. We'll only have as many bit lines as there are bits per word, but we're going to have as many word lines as there are unique locations inside the part or the chip. Now that's going to be a problem. We'll revisit that soon. For density and cost and even low power, we want, generally speaking, small transistors. So we don't want to have super beefy pass transistors or transistors in here. They're going to drive these bit lines, because these bit lines can be very, very long, right? In this case, 256K cells of bit lines. We want to be able to determine, and this is a large amount of capacitance on these bit lines as well. We want to be able to both write quickly without driving all this capacitance. We also want to be able to do a read fairly quickly. So what typically happens is, one trick is to pre-charge the bit lines. Pre-charge them to VDD over 2. And then, whenever we do a sense, we do a read, we don't have to wait for something to go to 0 or something to go to VDD. We just have to note what? That the bit lines that have the same voltage, right? Here's bit line and here's bit line complement. This one's voltage is starting to go up and this one's voltage is starting to go 0. As soon as, metaphorically speaking, we begin to see daylight between this voltage and this voltage, we now know what? Whether we've got a 1 or a 0. We don't have to wait for this to reach its high. We don't have to wait for this to reach its low to say, oh, okay, that was a 1. Okay? As soon as those voltages begin to diverge by a noticeable amount. Okay? Now, the other trick is that we want to try to avoid those long bit lines anyway, and we'll talk about how we do that in a moment. So let's look at the internal organization for a multi-word, multi-bit per word SRAM, hypothetically. So on the right-hand side, we have 4 address bits coming in. So right now, you know, we can address how many different words? 2 to the 4, 16, right? So we're gonna have 16 word lines coming out of this decoder. So n bits go in, 2 to the n come out. So we encode the word in binary, the address, and out of it comes a unary encoding, word 0 through word 15 word lines. Notice that we've got data coming in, D0 through D3, so this is a 4 bits per word and 16 words. And we have a write enable signal coming in, so we can do writes. We do reads, we're just reading the data out here at the bottom. And sense amplifiers are the devices that are able to detect these signals. When they're at VDD, they're like this. And then we do a read, and one of the bit lines, let's say the negative one, and the other one would be the positive one, they're gonna start to go like this for a 1, or this for a 0. And that sense amp is able to sense once they're far enough apart and go, ah, 1, oh, 0, okay? And then each of these is that SRAM cell that we saw before, those back-to-back inverters, okay, with the pass transistor. Now, imagine that we have 256K words, right? These bit lines are going to be phenomenally long. We're going to have drivers up here that drive values in, but those are going to be pretty beefy, right? They have to drive the full length of the bit line and overcome the capacitance on the bit line. Now, I promised you that we'd talk about dual-ported memory as well. The cool thing about doing dual-ported memories is that, in essence, you replicate everything except the actual storage cell. So we still have, if we have a dual port, then we have 2 address ports coming in, right? So each address port has to have its own decoder, right? Because if I'm accessing register I here and register J here, I have to decode this, say, 5 bits into 32, right? 5 and 2 to the 5, if I have a 32 registers. And the same thing here, I've got a 5-bit value for the address, R sub J, and I'm gonna generate 32 different signals coming out for the word selects. I also need, because I'm gonna select different words, I need different read-write logic. So I have to have separate, what? I have to have separate write drivers, and I have to have separate sense amps for the ports. So I'm replicating everything except the actual contents of the bit. And I have to have separate data ports, right? Because I'm going to be able to read n bits for register I and n bits for register J concurrently at the same time. The only thing that isn't replicated is the cell array. So here are my cells, right? There and there. But I have to replicate the pass transistors because I have 2 write lines now and a pair of bit lines because of 2 ports. Okay, so there's my word select, and here's 2 ports coming out. So I can independently address 2 things at the same time, but I'm still only storing the data one time. How are we doing on time? Sounds good for another 5 minutes? Of course you are. All right, let's take a look at a basic SRAM device. When we describe a device, it's very important to understand 2 really key things: the organization of the device and the capacity of the device. The capacity of the device is usually expressed as bits or megabits or gigabits or kilobits. So either bits or k-bits or etc. Capacity of a device. Now, if we're talking about a device, and by device I typically mean a chip. If we're talking about the capacity of a memory module or a memory system, or how much memory is in your computer, then we're probably going to talk about bytes and not bits. But when we talk about devices, by which we typically mean a chip, okay, we're talking about bits. The organization is expressed as the words or number of uniquely addressable locations and the access width. So in this example here, how many address bits do I have? Those are A0 through AN-1. There are n of them, right? There are n address bits. So how many unique locations or unique words are there in this RAM?
2 to the n.
2 to the n. How many data bits are there? I have separate bits for data in and data out, but there are how many?
B.
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 So the organization of this chip is 2 to the n by B. Again, Indian students might say 2 to the n into B, but we would probably say 2 to the n by B. That's the organization. The capacity is the actual product of that. So when you multiply that, that's the capacity. It's important to realize that two devices can have exactly the same capacity, but different organizations. For example, I can have two 1 megabit memories, one of which is organized as 256K by 4, 256K words or unique locations of 4 bits each. Another device, same capacity, 1 megabit, could be organized as 128K words or locations, each of which contains 8 bits, okay? This is crucial. This is vital that you understand capacity and organization and understand that we express capacity in bits for devices. Now the control signals are often active low. So notice our friend chip select from before, right? So when chip select is low, it means what? I'm talking to this device. If chip select is high, then this device is not even activated, okay? It's not driving its outputs, for example. Its outputs would be tri-stated. And that's very important, as we'll see in a few minutes, because we need to build larger memory systems out of smaller memory chips. So chip select is the essentially, I'm talking to you signal to the device. And if I'm not talking to that device, then it tri-states its output. And then we've got write enable that says, if it's low, then I'm doing a write operation. So I'll take the value on DN and write it into the location indicated by the address placed on the address lines, okay? Now there are some variations on SRAMs. For example, sometimes we trade pin count for higher performance. You'll recall that in the 8088 versus the 8086, which IBM chose for the first PC, the main reason for that was pin count. They wanted things to be cheap. So lower pin count for the chip, lower number of bits in buses, simpler IO devices, and so on. If you don't go that route, you can use the same pins for both input and output. So here we have dedicated input and output pins. If we don't have dedicated input and output pins, what does that mean? That means that when we switch from doing a read or a write to the device, we're switching who's driving those pins. So when we're doing a write to the device, we're driving the pins. When we're doing a read from the device, we're reading from those pins. So when we're writing to those pins, what's the device doing internally? It's got a device driver, a driver out here, right? It's got to turn it off. We don't want the memory trying to drive the contents of memory out to those pins if we're doing a write operation into the memory, okay? Likewise, if we're doing a read, we do want the driver to drive the contents of the memory onto the data pins, and we want to avoid trying to drive in. This is sometimes called turnaround time or bus turnaround time. We're turning around the direction. So we're going to sacrifice some performance for cost. We will multiplex these pins, if you will, or use them for both inputs and outputs. The other thing is that we now need this additional signal. I've given you different expressions depending upon whether we think of it as being active high or active low. Oftentimes output enable is active low, signaled this way, sometimes with a stroke. And as I mentioned, sometimes with a pound sign. So we control that. So if we're going to drive, we're going to do a write to that device, then we want to make sure that output enable is disabled. Okay, if output enable is active low as signaled by the bubble on the input, then we keep output enable high. And we're doing the write. This driver is turned off and there's no bus contention or bus conflict. Now, when we want to do a read from the device, we stop driving. We turn our driver off if we're the memory controller or the processor. And we now bring output enable low, enabling the RAM to drive its value out to the D pins where we read them. So that's how output enable works, okay? Not necessary if you've got separate D in and D out pins. You know, our timing couldn't be better because next up is a, a quiz or a poll I had set up. Because the overwhelming, well, that wasn't true. I wouldn't say overwhelming, because the majority of people would prefer not for credit in class assignments, although there was a fair number. We'll do this as an in-class, not for credit quiz. And then we'll take a break. So this is to wake up before you go on break. Let's see if I've done this correctly. I did. All right, so I've depicted here a hypothetical memory device. Assume this is a hypothetical chip. Okay, maybe it's an SRAM chip, as shown here. I want you to answer a couple of questions about this device. The first question, what's the organization of this chip? How is this chip organized? Anyone?
Or how are we responding?
Well, you know, that's a good question. You may respond, let's see if I get back to the right window here. You may respond by, if I could locate it again on my screen, you could respond by chatting. But my chat line just went away. Here we go. All right. Somebody said the organization is 2 to the 19 times 8. That is correct. Anybody know what 2 to the 19 is? Remember our powers of 2?
512K?
What would 2 to the 20 be? 2 to the 20 would be 1 meg, right? So 2 to the 19 is half of a meg, which is 512K. So excellent. This is a 512K by 8 device. Fantastic. Whoops. So we could say I've got a 19-bit address. It's 2 to the 19. 2 to the 19 is 2 to the 9 times 2 to the 10. 2 to the 10 is K. 2 to the 9 is 1/2 of a K, or 512. So that should be fairly easy to do in your head. And we've got 8-bit data. So it's just 512K by 8. So this is how you would write it. Not 512KB by 8. There's not 512KB here. There are 512K unique addresses. So be very, very careful. This is not a 512KB by 8 device. Remember to keep your units. The units of addresses are just unique addresses. Okay, this is really important. Okay, it's 512K words or unique addresses times 8 bits per word. Okay, now what's the capacity of the chip? Okay, the capacity, we just do the multiplication, right? 512K locations times 8 bits. Another way of saying that is that's 4 times 2, which is 8, times 512. Why did I write it that way? Because 2 times 512 is 1K, and 1K times 1K bit is 1 megabit, and then times 4, so you end up with 4 megabits. Now I'm talking about capacity. I am talking about bits. Okay, not 4 megabytes, but 4 megabits. So 4 MB like this would be a wrong answer. Uppercase B is bytes. We're expressing capacity as 4 megabits. Okay, why don't we take a pause here? I have 101. Why don't we do a 9-minute break? You guys have sat through nearly an hour of lecture and just did a short in-class exercise. I'm comfortable with a 9-minute break. I will pause my audio and video for at least the first 5 minutes, and then I'll come back early in case anybody has any questions. So I'll be back on in 5 minutes, but we'll start lecturing again in about 8 minutes from now. Okay, I'm back and I'm available to answer any questions or deal with any other issues before we resume lecture in about 2 to 3 minutes.
I have a question.
Yes, go ahead.
So in the dual ported memory slide, you noted on the bottom that there's a conflict if read and write of the same word on different ports.
Actually, I didn't note that, but go ahead.
No, I mean, the slide notes that. You didn't say anything about it.
Uh-huh.
I was wondering what causes the conflict.
Oh, that's a good question. Let me flip to a blank page here. So imagine that we have a pipeline processor, as almost all processors are, and we've got something like add R1, comma, R2, comma, R3. And a little bit later, we've got an instruction like add R4, comma, R5, comma, R1. And we'll talk about exactly these kinds of issues in 586 and 486, but suffice to say, this instruction earlier in the pipeline has already done its add. So here's the ALU, and it's done its operands, and out comes the result, and it wants to write this into the register file. So here's the register file. And it wants to write into R1. That's the address it's providing on the write port. And that's the write port, and here's read port 1 and read port 2. And now along comes this instruction later. This is the earlier one. This is the later instruction. So the first instruction, the earlier one, is completed. It just wants to write the result back to R1. During the same clock cycle that it wants to write R1, this instruction is being executed, and it's at the point in its operation where it wants to retrieve R5 and R1. So it puts the value for R1 and the value for R5. That is the encoded value for 1 and 5, right? Well, here's a problem. Inside the register file, we're attempting to both write and read R1 during the same clock cycle, and that would cause a problem. Now, we don't want to stall the pipeline because these kinds of things are not that infrequent. So the way some pipelines deal with it, and we'll talk about this in 586, is that writes happen during the first half of the clock cycle and reads happen during the second half. So we process writes here and we process reads here. So in the first part of the clock cycle, the earlier instruction is allowed to write its R1 into the register file. And in the second half of the clock cycle, we're able to read data out from the first read and the second read ports. It also has the advantage that we're able to do what? We're able to get the newly written value of R1 out of the register file. Does that answer your question?
Yes, thank you. Part of my confusion was when I read same word, I was thinking of the same like data value as
okay.
opposed to same address. That makes
same address,
a lot of sense. Yeah.
Yeah, the
Thank
same
you.
location, the same word inside the. All right, so what would be the sense of coming back from a break without doing a quick poll?
Mark,
Yes.
I have a follow-up question about Seth's question.
Yes.
If you do the reads in the second half of the cycle, doesn't that make doesn't that require you to have like a much tighter control over like setup and hold times for the registers that you're going to be putting the read value into?
You know, that's very implementation and technology specific, but if our register files are address following, then for reads, it's very forgiving. We can actually place the numbers here, right? Those are 5-bit values, right? We can place the value for encoding 1 and 5 on the 2 read ports, and we may have junk out here during the first half of the cycle, right? But then during the second half of the cycle, these will contain valid values. So we do have to have, you know, tight timing control. but we don't really have to worry too much about setup and hold time for the purposes of read operations. So the reads are more forgiving. They're just simple address following.
Okay, I guess I was maybe more referring to like the effective writes to the target registers in the ALU.
Yeah, they will in fact determine in many cases the length of a cycle, the register file access.
Okay.
Yep. Okay, it looks like most everybody's voted. I'll end the poll, and everybody said, wait, there's lecture today? No. Good. All right, so it sounds like the pace is pretty good. There are a few folks who found it a little bit fast. Again, I would encourage you to see me or Ruchit during office hour, or feel free to check in on the discussion thread in detail. But it looks like we're kind of hitting the sweet spot here. That's what I need to know. And get rid of that poll. All right, we'll return to the lecture. I'm going to now show this SRAM timing diagram in a somewhat more techie kind of way, kind of the way you saw the 8086 timing diagram, and that's on purpose. So here's our write enable. We're going to look at a read cycle. Write enable, as you can see with the overbar, is active low. So if we're going to do a read, we would keep write enable high. Write enable is asserted low. That is true when low. So in this case, just adjust my chair here. Okay, so in this case, if we're doing a read operation, we would keep write enable high. Active low, therefore off when high. Chip select is also active low. So we're not even talking to that chip as long as chip select is high. We want to do a read, what do? We simply place what? A valid address on the address lines at this point. Here, it's either the previous address we were reading from, or we weren't even doing a read, we didn't care. Then we bring chip select low, and now that device is selected. And so sometime after we've provided the valid address, we will see valid data come out. Now, really, it's sometime after we placed the valid address and brought chip select low. By the way, we can bring, in most devices, it's okay to bring chip select low earlier. It just means that what we'll be seeing on the output is not yet valid until we've placed the valid address. Understand? So, drive a valid data address and assert chip select. And after some amount of time, which is known as the access time, we'll see the correct data. Now for writes, we'll start out with write enable high and chip select high. We have to place both valid data and a valid address, okay? And then we bring write enable low and we bring chip select low. And some amount of time after that, the memory cycle completes. Now there are rules that say how much longer after write enable goes low or chip select goes low do we have to hold it in order for the write to actually take place. And during that time, of course, we have to continue to hold the valid address and the data. Obviously, if we start moving data bits around here, we're going to write junk or garbled data into the device. So we have to keep address and data in stable throughout the write cycle. Now, a couple of key things. Access time is the time from when we have a valid address till we get valid data output. Remember, there's always going to be signals on that output unless there's an output enable signal that turns them off, right? It's just that those output bits don't mean anything if the address bits are changing during that time. Now, if we make things simple and say that chip select goes low and address is stable at the same time, then from whenever that time is to when we get data out, that's our access time. Okay. Now cycle time is different. Cycle time says after I do a write, how long until I can do another one? Maybe I want to write another byte. So now I want to wait some amount of time, bring write enable and chip select low, and out here place another valid address and another valid data for another write. That's cycle time. And that's the time between memory operations. And then we've talked about setup time and hold time. Setup time is the time that the address and the data had to be valid before write enable goes low. We have to set it up prior to that time. And then how much do they have to remain, ooh, a little bit of a typo there. How long do they have to remain stable after they are no longer low? So setup time is time prior to a critical edge. Maybe it's a clock edge, right? So if this is a clock edge or a write enable, setup time is the amount of time prior to, and hold time is the amount of time after that we have to keep the other signals stable. Okay. Now, let's look at typical SRAM timing in a little bit more detail here. In this case, I'm using bidirectional data signals. So I have to use an output enable because that determines whether or not the chip is going to be driving the output data. So for a write, who's driving the output data? Or something, who's driving the data signal? The memory controller or the processor is driving the data signal. So we're going to keep output enable high. That is, disable it. We don't want the device driving that data. We are going to drive data in because it's a write operation. So we place valid data on the data in lines. We place a valid address on the address lines. We keep output enable high, and then we take write enable low. This amount of time that data in and write address must be stable prior to write enable going low is the write setup time, that distance right there. Okay. Now we start the cycle of writing and we bring write enable high to end it, but we still have to maintain valid data in and valid address some amount of time after write enable goes high. That's the hold time. That's this distance in here. Now, at some point, we want to do some other operation and we might have to wait for the cycle time. In this case, we're going to do a read. Notice, by the way, what we did with output enable right here. Output enable is still high. At this point, when we, the processor, turn off our driver to the data, nobody's driving the data signal. I didn't draw it. Here's our processor. We're capable of driving that signal as well, right? It's bidirectional. We turn off our driver. We're no longer trying to drive. We're no longer trying to do a write. So it's tri-stated. We tri-state it, so did the device because of output enable. But then what happens? We bring output enable low. At that point, this chip is now driving the output data. Did we give it a valid address? Not yet. It's just junk. So what do we see on the data? Junk. Is it really junk? Well, it's whatever random location the current address bits are referring to. We don't care. Now we place a valid address, and some amount of time later, the read access time, because this is just address following, we see the data at that location present on the output pins. And then we can change the address and read from a different location. So some amount of time later, we see data out for this corresponding address. Now, what we could have done is we could have kept output enable high a little bit longer and dropped it here. What's the difference? The difference is that internally, the read is still happening, but what's happening in the output? It's still tri-stated. And only once output enable goes low, I'm sorry, I did the wrong line there, whoops. If we hold output enable high for a little while longer, then, and bring it here, then this will still show junk. What if we bring it out to here and bring it down? Well, then this amount of time, the data is available internally to the chip, but it's not able to drive it yet because we have output enable turned off. So we'll still see tri-state or Z all along in here. As long as we keep output enable high, this device will be driving tri-state out. Okay, only once we enable output enable will we see something come out. And if we waited long enough beyond the read access time, then what comes out will be in fact the valid data at the appropriate time. Now I'm going to show you a very simple example, but it's from a real part. It's a Cypress SRAM. Cypress was an SRAM, among others, manufacturer. And this is simple address following. You see the address, we change the address here. So now we have a valid address. And whatever data was on the data output corresponded to this previous address back here. And some amount of time, because we just changed the address bits, internally what's happening? The decoder has some delay, right? There may be unequal path lengths inside, so some of the address bits are changing just a fraction of a nanosecond before the others. So the output out here is not random, but it's not reliable. Then after the access time, we now have valid data coming out on the data out that corresponds to this address that we placed here. Notice the name for this, it's T sub AA. So from when we've got valid address to we get valid data is TAA, that's the access time. How long does it take to access the chip? That's latency. Access time is latency. Now TRC is the read cycle time. That's the minimum amount of time between memory operations. So that basically says if you want to change the address again, you've got to wait TRC amount of time. And then you can place a new address. And then after TAA, you'll have new valid data come out. Now, RC, read cycle time, is bandwidth. That determines how frequently I can get data. Those are two different things. So if I have to fetch data repeatedly because I'm trying to drive a processor's instruction stream, then I care a lot about bandwidth, right? I need to be able to keep getting data at a certain rate. Latency matters, but it's not as important. It just says I wait longer to get the first piece of data, but then I get it what? At the rate that I want it at, okay? Let's take a look again at this internal organization. Let's return to this. This is all fine and good, right? What happens though when the number of address lines gets to be, say, 15 or 19? In other words, I've got what coming out of here? I've got 2 to the 19 or 2 to the 15 individual select lines coming out. Do you think that's realistic? Those are big numbers, right? 2 to the 15 is what? 32K. Roughly 32,768 or whatever word lines coming out. That also means that these bit lines are going to be really, really long, which means these drivers have to be pretty beefy and my delays are going to be longer. So in reality, guess what happens inside a memory chip when we start to have a lot of addresses compared to few bits wide? We cheat. Whenever the number of addresses gets really big, right, here's the number of address bits coming in, we're going to have really long bit lines and we're going to have a really big decoder. Everything is going to slow down. So the solution is to make it shorter and wider. So inside every DRAM or SRAM that appears to be tall and thin is really one that's approximately square. How do we achieve this? We cheat. So let's say we've got an n-bit address. What we do is we make k plus m equal n. And they won't always be exactly equal, but we'll try to make them basically be equal. So k equal to m equal to n over 2, approximately. So we'll take this n-bit address and we'll arbitrarily say, well, let's use the upper k bits of that address. There's n bits. Let's use k bits as a row, and then let's use the m bits here as a column. And then we have a decoder here. And what we do is we access, in essence, an entire row, right? Read that row into the sense amps, and then have a multiplexer that's controlled by a decoder on the column address, and out comes the 1 bit. So in other words, we do kind of like an XY, right? We grab a row corresponding to the k bits of the address, the row address, and then the m bits determine the column. And now we can make this array be approximately squared, so we've balanced the bit lines and the word lines. Beautiful. You're probably saying, but wait a minute, I don't want a memory that's 2 to the n by 1, because that's what the organization of such a memory would be, right? Right? I have n address bits and only get 1 data bit coming out. No problem. You know what we do? We replicate the bit planes. So these bit planes, if you wanted really 2 to the n by, let me get the right thing here, 2 to the n by 4. So you want a memory that's 2 to the n by 4. We'll take our n bits, break them into k for row and m for column. And this is the cool thing. We don't need to replicate the decoders here or the mux. Why? Because we're using the same k bits to access each of these 4 planes of memory. Each one of them will yield up 1 bit in depth here. but we use the same K and the M. So if we want this bit right there, right, then we're going to activate that in all 4 of these planes. And then when that bit comes out in each of these 4 planes, we have 4 different sets of sense amps, right? 1 set of sense amps for each plane of memory, and 4 multiplexers, but the same set of address bits are selecting the same column in each of those 4 planes. So out comes now 4 bits. Now this is sort of 3-dimensional, if you will. Obviously it's going to be 4, and then they'll be try to equalize the bus length and all of that. But that's how we get, say, a 2 to the n times 4 memory in a mostly square kind of memory array for efficiency's sake. Is that clear? So inside, when you pry off the lid of a chip for memory, even though it might be organized as like 256K by 8, what it's really going to do is they're going to take 256K is how many address bits? You guys should be able to just do this like this. Right? 18 address bits. So generally speaking, we'd probably go with 9 bits for the row address, 9 bits for the column address, and we would have 8 of these identical planes. That's how we would build a 256K by 8 memory chip. Understand? Okay. So, as I said earlier, we've got memory chips, but we want to build memory systems. Maybe we want to build DIMM modules. Maybe we want to build memory right on a board or whatever. So how do we build memory systems using memory devices or memory chips? Let's take an example. Here's a 64K by 8 RAM. That tells us what? Its organization and its capacity. And if you are unsure, you can look at what? The width of the data input. It's a by 8 data coming out, 16 address bits, and 2 to the 16 is 64K, right? By the way, does everybody know what that symbol means there? It's a symbol that's commonly used to indicate that the output is a tri-statable output, or tri-statable. Tri-statable. And we know that because there's the chip select. So if chip select is not selected, in this case, chip select is active high. If chip select is low, the device isn't selected, then what will be on the output data? Tri-state. Okay. Got it? So we know the organization. What's the capacity of this chip? $64K by 8, right? If you're not good at the math, you can just think double 64 once, 128, double it again, 256, double it again, 512. So it's 512 KB is the capacity. Okay. Oops, did not mean to do that. All right, so let's say we want to build a 256K by 8 memory subsystem here. How many address bits do we need? Well, I've done the math for you already. 256K by 8, and this is a 64K by 8. Well, 256K would be 2 to the 8 times 2 to the 10, so I'd need 2 to the 18 locations. I need 18 address bits. So how many 64K by 8 RAM chips do I need? $256K divided by 64K equals what?
4.
4. Because they're all the same width. I still want to buy 8 memory subsystem, right? So I need to grab 4 of these chips in order to do what I want. And here's a design for doing exactly that. Here are the 4 chips. Notice that the outputs are all tied together because each of them contributes 8 bits, but 8 bits is all I want. So these outputs are tied together on the same line. If these were not tri-statable, I would have a contention or conflict. So what does that tell you? It means that only one of those chips will be chip selected at a time. So what we've basically done is we've taken our desired 256K by 8-bit memory, and we've essentially split it into 4 banks, where each bank, and this is the most heavily overused term in memory systems, the word bank, but each bank or subsegment is accommodated by one of these chips. And this one is here, and this one is here, and here. How does that work? Look at the address lines coming in. We needed 18 address bits, right? So A17 down to A0. There's our address. Okay, A17, A0. We're going to take the most significant 2 bits, and they're going to go into a 2 to 4 decoder. And the memory enable just says, are we doing a memory operation at all? So it's a decoder with an enable, otherwise known as what? A demux, right? If you're not familiar with that. A demux or a demultiplexer is a decoder with an enable signal. So the 2 most significant bits here and here drive a decoder. What happens if the 2 most significant bits are both 0? Then the 0 output of the decoder is a 1. And what happens then? We chip select this one, which is the low order address bit. So this responds to addresses from 0, 0, all zeros to 0, 0, all ones. What happens if the most significant bits of the address are 0, 1? Then the 1 output of the decoder becomes true, and this chip is chip selected. And we're now talking about memory ranges between what? 0, 1 and all zeros to 0, 1 and all ones. So this chip accommodates that memory range. What happens when the input address most significant bits are 1, 0? Then the decoder's output 2 is enabled, and that enables this chip select, and we're talking about addresses in this range, which is what? Addresses between 1, 0, and then the rest zeros, to 1, 0, and the rest all ones, which are in there. Then finally, if both address bits, most significant address bits are both 1, then this output becomes high, and we're talking about this chip select, and we're talking about this last portion of our memory address space, and that responds to addresses 1, 1, all zeros to 1, 1, all ones for the remaining address bits. Now, what about those remaining address bits? We only use the most significant bits to drive the decoder and therefore do the chip select, right? So what's happening with the remaining bits, bits A0 through A15? They go into the address lines of all the chips in parallel. But wait a minute, only one chip is responding, right? So what are the other chips doing when their addresses have these other address bits on them? Nothing, because their chip select is low. They're deselected. So they're all ignoring the address bits on their input and the read-write signal on their inputs, unless their chip select is enabled. And then and only then do they respond to the address that's on their address lines. Notice the input data, if we want to do a write, goes to all of them as well, okay, because they share those inputs. We can't write to this piece of the memory and this piece of the memory at the same time, for example. Okay, so basically we have in essence, it's kind of a multi-banked memory, or partitioned. We've taken our address space of 256K and broken it down into 4 64K pieces, each served by a different by 8 device. Clear? Well, what if we want a different kind of memory? What if instead of 256K by 8, what if we want a 64K by 16? Well, 64K, these chips are already 64K. That means what? We don't have to do any special address decoding. But instead of 8 bits, we want 16 bits. So what's going on now?
We
Well, how
can-
many address bits do we need? Same as before, right? 16. How many chips do we need?
2.
Right, we need 2 chips. In a moment, I'll figure out how to get this back into the right mode here. Oh, well, we'll do this. Look at what we're doing this time. Now, we basically want a 16-bit data bus. So now the chips are going to be sort of side by side. We're not going to wire their outputs together because they are each going to contribute a different 8 bits to the 16 bits that we want. So in other words, now we're going to place the same address to both chips, and we're going to give them both the chip select at the same time because we're going to fetch 1/2 of the 16-bit word from one chip and 1/2 of the 16-bit word from the other chip. So now we've got a configuration that looks like this. Same address gets presented to both chips, and they each give us 8 bits out. And then together that gives us the 16 bits that we want. We can't independently read at one address in one chip and one address in another. That would mix the bytes that we're looking at. So notice that the 16-bit address goes to both chips. Their 16-bit inputs are split. 8 bits go to one chip, 8 bits go to the other chip. The chip selects are tied together because we're going to enable both chips at the same time. Okay. This gives us another term in our very rich terminology for memory, and that is the term rank. A rank is a set of memory chips that share the same address control and chip select signals, with each chip providing a subset of the data bits required. Now, in the previous example where we used 4 chips like this, those were not part of the same rank because they didn't do what? They didn't share the same chip select. So how many ranks were present in that first example? 4. There were 4 different ranks, 4 different sets of unique chip selects. How many ranks are present in this example? 1. Together, these are a single rank, okay? They're each sharing chip select, and they're working in lockstep to give us different parts of the 16-bit word that we want. Okay? It's quiz and poll time again. We'll do this as an in-class exercise. How's that? All right, so here's a hypothetical memory system that I'm creating from 512K by 8 memory chips. So you see down here, there's my 512K by 8 chip. Each of these up here is one of those 512K by 8 chips, okay? Give you a chance to look at that. Okay, the first question, what's the organization of this memory system? Not the chip, what's the organization of the memory system? Whoops, I'm going to actually have a chance to do that. How would you figure that out? It's how many unique locations there are, right? How many unique locations are there in this system?
2 to the 21.
2 to the 21 is a 21-bit address. So I've got 2 to the 21. And then how wide is a memory access?
32 bits.
32 bits. Remember, it's 32 bits, right? So we would describe this as a 2 to the 21 times 32, or what? What's 2 to the 20?
1 meg.
1 meg. So 2 to the 21 is 2 meg. And if you want to be really use the new terminology, it would be 2 meg by 32. Okay. What's the capacity of this memory system? Well, you just do the math. you could say that it's 2 times 32 or 64 MIB, right? 64 megabits, right? And that would be perfectly fine. But since it's a memory system and not a memory device, we might choose to do what? And get the answer expressed in bytes. 64 divided by 8 is what? 8. So it'd be 8 MI uppercase B for bytes. Okay? Your choice. Okay? Very important here. If it's word accessible, which this one is, this is not a byte addressable memory. When we access something in this memory, we are accessing a 32-bit word. So a lot of folks might choose to keep it simpler. Okay, you might talk about the organization instead. How many ranks are there in this configuration? There are 4, and then here's one of them. There's a rank. Why? Each of these 4 chips will all be chip selected at the same time. Do you see the high order bits of the address coming in here, A19 and A20? They go into the decoder, and then one of the select bits comes out here and drives all 4 of those chip selects. So that's a rank. These constitute a rank. These are a rank, and these are a rank. Okay. So basically our memory has its address space divided into 4 chunks, right, based upon the upper 2 bits of the address, and plus each piece of a given place is served up by a different chip in the rank. Okay, this is fundamental to understanding memory systems. All right, now getting back to that notion of cycle time versus access time. Do you remember that Cypress SRAM timing diagram? T sub AA, access time, says I make my request here, I get my data when? Here. T sub AA, or access time later. But I can't come back and ask again until what? Not T sub AA, but T sub RC is when I can make my next request. Okay. Typically, memory cycle times will be greater than, maybe much greater than access times. Okay. Now, the analogy that I sometimes use, my son doesn't like hearing this anymore because he's now out of college, but when he was young, he used to get an allowance. He could basically get a weekly allowance. Okay. That was essentially what? Bandwidth, right? That's his cycle time. How often can he ask for his allowance? Once a week, right? That's bandwidth. In other words, if you wanted to know how much money he could get in a year, bandwidth answers that question, right? How many times can he ask? Times how much does he get each time, right? That tells you what his annual allowance is. So that would be cycle time, and that determines bandwidth. Now, latency is when he asks, how long until I give it to him? Well, that's virtually instantaneous. If I have money in my pocket and he says, hey, can I have my allowance? I say yes, and I give him his allowance. So the latency here is very low. The bandwidth is weekly. Okay, my son is not a fool. So what does my son do? On Wednesday, my son comes to see me and says, can I have my allowance, please? And I say, yes, here you go. And I don't expect to see him again until when? Next Wednesday. In fact, if he comes before then, what will I do? I'll remind him that I only give him allowance once a week. But he's not dumb. So what does he do when Sunday rolls around? He asks his mother. And his mother says, I haven't given you allowance since last Sunday. So sure, here's your money. And don't come and see me again until Sunday. But then on Wednesday, I see him again and he says, hey, you haven't paid me my allowance in a week. And I say, you're right, here it is. What has he just figured out? He's figured out a way to increase his bandwidth without changing latency. Do I respond to him any faster? No, neither does his mother. But he gets twice the bandwidth. He's basically invented a really clever concept called interleaving. So this is what would happen if he came to see me. He asks, he gets his cache. Now he has to wait until a week goes by, that's this, and he asks, and he waits a few seconds and he gets his cache. But what he's effectively able to do is that after he gets his cache from one parent, he can now immediately go and ask another parent, and he only has to wait for the latency to get the cache from that one. Okay, now if he had 4 parents, he could really exploit this system. And this is the way interleaving works in memory. So in other words, I make a memory reference and I've got no choice. I can't get around latency. So I make sure that my first reference goes to memory bank 0, and I wait this amount of time here in red, and I get the memory data I'm looking for. Now I can't go back to memory bank 0 until here, my cycle time. But I can immediately go to bank 1, because I haven't talked to it in a while, and request data, and I get the data right here. And then I go to bank 2. I make a request to bank 2, I get the data here. Then I make a request to bank 3, and I get the data here. Now, what's happened? I'm well past the time for the cycle time of bank 0. I can go back and access bank 0 again and get data from bank 0. Now, I haven't improved the latency of any of these 4 banks of memory. They're the same. But I've improved my bandwidth by a factor of 4 times. Okay? This is the magic of interleaving. I think we will actually stop here. And I think when we resume on Thursday, we'll begin with a small group activity around this concept of bandwidth and so on. I think that makes sense to me. Any questions on what we've covered so far? Yes, Nick, you're right. or kids who are adopted and have both birth parents and adoptive parents. No questions on today's lecture?
I've got a quick clarifying thing. I assume it's implemented in hardware, but when we're talking about like wait times and hold times, is there anything specific you have to do if you're like from the programming perspective in C or assembly, or is that all hardware handled?
That's a great question. That's all done in hardware. That's typically in the memory controller or in the hardware design.
Okay, that's what I assumed.
Yep. You want to go back to the last quiz or poll? This one. Let's see, the organization of the system, that's just the number of unique addresses times the width of one data access. That is, how much data do we get at a time. How many unique addresses? Well, we see right here, there's a 21-bit address. There's a 21-bit address. You see A0 through A20, right? So 21-bit address means I've got 2 to the 21 unique locations. And each unique location gives me what? 32 bits at a time. So I've got a 2 to the 21, which is 2 to the 1 times 2 to the 20, which is 2 meg addresses, times 32 bits of data. So the organization is 2 meg by 32. The capacity is just the product of those two, right? Number of unique locations, amount of data in each location. So 2 times 32 is 64. That's 64 megabits, but oftentimes if it's a system and not a chip, we might express the capacity in megabytes. So 64 megabits times 1/8, 1 byte per 8 bits. So bits cancels and we get 8 megabytes. Don't do that for chips. Chips, even large chips are expressed as bits in their capacity. Now I asked how many ranks there are. Recall that a rank is a set of chips that share the same chip select which means they'll all be active at the same time. And that's because they're each serving up or delivering a subset of the full size word. Now this memory system wants to read words, okay, of 32 bits, but the chip that we're dealing with only gives us 8 bits. So what do? We use 8 of them in parallel. That is, they have the same chip select. So if you look at the 2 address bits that are the most significant going into this decoder, they determine the chip select. And that means that each of these will be selected at the same time, each serving up 8 bits of a 32-bit word. So I need 4 of them. So there are 4 ranks, and here's one of the ranks, it's shaded. And there's another rank here, another rank, and another rank. So 4 ranks, each of which have 4 chips. Okay.
On slide 26, can you just explain one more time for me how we get the 512 qubit capacity?
Sure. So slide 26, you said? Am I at the right one?
Yeah, you're at the right one.
Okay. So here I said I want 256K by 8. Okay, and I'm going to use these 64K by 8. Well, I've got the right width, right? I only need a by 8 device, so I'm good there. But instead of needing 64K locations of 8 bits, I need 256K locations, right? So I'm going to need 256K divided by 64K, which is 4 chips.
I meant the capacity. On that slide when we were there, we said it was 512 qubits, and I didn't understand that.
Of 512 for the device or the memory subsystem?
For the memory subsystem. Or maybe I wrote it down. Maybe it was meant as for the each device.
Well, we can actually compute that. Let's go back. So the capacity of this device, I could do the math. 64K doubled once is 128. Double it again is 256. Double it again is 512, right?
Yeah.
Or you could say 64K is 2 to the what? 16, right? Times 2 to the 3, right? Equals 2 to the 19, right? And 2 to the 19 is 512K. So it's 512K or 512K bits.
Okay, I think I got confused because I thought it was a question about the memory subsystem, but now I understand it's for each device.
Yeah, and here when I was asking about capacity, it was for the device.
Okay, awesome. Thank you.
Yep. Any other questions? Okay, let's see. You have a homework due on Thursday. I'll be checking the D2L discussion threads if people are having issues or questions. I have office hour on Thursday morning. That office hour link is now in the start here portion of the content on D2L, so everybody can get to it. I also emailed it to you. And I will begin Thursday's lecture with the topics that people said they wanted a little bit more time on, which was, remind me, it was asynchronous handshaking. And what was the other one?
Nested interrupts.
Repeat, please.
Nested interrupts.
Nested interrupts. Okay. Or if you like, I can talk about them now. Since we're recorded, people can drop off. What do people want to do?
Oh, I have a quick question about homework.
Hold on just one second, Seth, okay? Akshay, do you want to talk about nested interrupts now, or you want to wait till Thursday? Or office hour? Okay, Akshay says now. All right, Seth, what's your quick question?
I just wanted to know if you could release homework 3 sooner rather than later.
Yes, but sooner rather than later is relative, but I will do that.
Thank you.
So I'll make a note to do homework 3. Okay. Again, you're not required to stick around. This is just going over topics we already went over, but in a bit more detail. So I'll briefly, I'll talk about, and if you can't stick around but you want to watch the video, it keeps recording. I'll talk a bit about nested interrupts then. So we're executing code. Here's our routine, right? And we're somewhere in the code and boom, an interrupt happens. So that takes us into a chunk of code, which is the interrupt service routine for this interrupt that just happened. Let's call it interrupt A. And we're executing this code. And maybe there's a higher priority interrupt that happens. So we interrupt the interrupt. And now we go off to another interrupt service routine for interrupt B. And we start executing that code. And then we do an IRET. I'm using x86 language here. We then return here, continue executing, hit an IRET, and then we return back to here. If that's not too confusing.
Is there any case where, like, after doing IB, instead of returning and really finishing IA, we would return to the instructions? Like, what if the thread that we were working actually turns out to be like higher priority after it's taking so long to do all of these interrupt servicing?
No, there are things called coroutines that work kind of like that, but no, we would always want to return from or to the place where we were interrupted.
Mm-hmm.
Now, let's say that you want to enable this. Let's say you don't want to enable this thing to happen. Let's say the scenario you want is that this cannot be interrupted. It's doing a high priority task and we can't allow interrupts while it's happening. Now, it's okay once it returns and hits its IRET and comes back up here. It's okay that that interrupt, which is pending, right? It didn't go away. That interrupt, which is pending, would now happen here and get us into the interrupt service routine, all right? So in other words, let's take scenario A. We don't want nested interrupts. Then what has to happen is when we take this first interrupt into the interrupt service routine for interrupt A, we have to immediately lock out further interrupts because we don't know when this other interrupt could occur. It could occur literally as we're starting to fetch this one instruction right here. We have no idea where it could occur. So we have to rely on the hardware mechanism to essentially turn off interrupts. Usually that's a global interrupt enable, i.e. if you prefer. Sometimes it's trap enable. Okay, turn them off. Do that as part of the hardware. Then, if this other interrupt, B, happens, it will be a pending interrupt until we return from the interrupt and come back to the original code here. Now, what if in scenario B, we do want nested interrupts? No problem. What happens now is we take the interrupt here and go into the interrupt service routine. The hardware automatically turns off global interrupts by clearing these flags, depending upon the architecture that we're in. But the very first instruction of this interrupt service routine can essentially be to turn on IE or TE flags and say, I would like to allow them. And now we continue executing and maybe another interrupt doesn't happen and then we just return. Or maybe an interrupt does happen and we take it and service that interrupt, okay? The point being that if we don't have the hardware clear those flags, we never have the option of making this scenario work reliably. Because if the flags are always enabled, then as soon as we take this, this would be required to turn off the flag, right? To prevent nested interrupts. But what happens if we're interrupted before we execute that instruction that turns off the interrupt flags? Then we're hosed. It's a timing issue, right? But it's certainly possible that we could be unfortunate enough to catch an interrupt right at that point in time. Okay. So we have to first disable them in hardware and then have the routine explicitly enable them among its first few instructions if it wants to do that. By the way, you'll encounter this if you haven't already in RISC and others. There's a special register that is pending interrupts. So for each potential interrupt, there's a bit that's a 1 if I've got a pending interrupt of that type in it. You may have come across that already. Akshay, how was that? Okay?
It was good.
All right. Somebody asked me to talk about asynchronous handshaking, and I'm happy to do that. I don't know how far back you wanted me to go in asynchronous protocols, but in the very simplest case, there's no handshaking at all. We just blast data. We're the sender, and here's the receiver, and we just blast data. But the only time you would do this is when you're not worried about losing data. So for example, the data is a single bit and we're driving an LED, right? And the LED flashes if we've got shines, or is illuminated rather, if we put a 1 out here. And is turned off if we put a 0 out here. Well, if we're sending out 1s and occasionally a 0 or a bunch of 0s and then 0, 1, 0, 1, the LED might flicker, right? But we're not causing a loss of data being transmitted to some other entity, right? Another example would be if we have like a 7-segment display, we're trying to display, example would be a scale or a temperature sensor. So you've got temperature or a weight value being transmitted on the data. And the receiver is just displaying that in a 7-segment display. Well, what happens if the temperature is fluctuating a little bit between 99 and 100 degrees? Well, the output will say 99, then it might say 100. If it's fluctuating rapidly, then it might glow a little bit or be a little confusing to look at until it settles in, all right? Same thing with a scale. When you first get on a digital scale, what happens? The readout's kind of all over the place, and then provided you're not moving too much, it will settle down, okay? But we're not gonna lose data as a result. Our display will just instantaneously, with some hysteresis maybe, respond to the data that's there. But in other cases, we need to basically say, I've got data for you, and I'm gonna signal that it's available. And in this case, we have a data ready signal, and we'll place the data on the data signal, and then sometime after, we'll assert data ready to say, hey, here's some data. And then you get a chance to grab the data, I deassert data ready, and then after me assuming you had enough time, I can place some more data and then make data ready go high again. Now, it's the source that's controlling this, and it's assuming the destination is keeping up. So I would never use a fast source and a slow destination. I would do just the opposite. So a keyboard is slow. I mean, the keyboard is limited to how fast a human can type, and none of us can type fast enough to keep a CPU or even a microcontroller busy, right? So if the source here is a keyboard and the destination is a microcontroller or microprocessor, then it's fine. The keyboard puts out an 8-bit value that is the encoded key that was pressed, and then says, I got data ready. And the processor, either through polling or even through an interrupt that gets interrupted when data ready goes high, grabs the data, puts it in a buffer or processes it, and does that all way faster than the sender has a chance to provide more data. So not a problem. You could switch it around and make it be destination controlled, in which case it's the source that should have no trouble keeping up. So maybe we make a request of the source and say, send me data. And by some agreed upon time thereafter, I get valid data. And then it has to be able to respond to me saying, hey, send me some more data, and giving me more data. Again, these assume there's no essential handshake or error or anything like that going on. Now, somewhat more sophisticated are the handshaking protocols. That was pre-COVID, we don't touch hands now. So in the non-interlocked, and these are request acknowledge, if we're the sender, we output valid data, and then we assert a data ready signal to say, hey, I've got some data for you. The receiver sees data ready go high and says, oh, you've got data for me. I will grab it off the bus and store it or process it. And then I'll signal to you that I've got the data by asserting data accept. When you, the sender, see my data accept, you know I've got the data, hence the causal signal here. So you stop transmitting and you're ready for the next transmission. So that's one complete transmission and you're ready to start sending data again. Okay. In half interlocked, it's a bit more reliable. Similar deal, I assert data or apply data, I assert data ready, and then the receiver sees data ready, grabs the data, asserts data accept, okay? The difference now though is that instead of data ready going low right away up here, once I assert it, we don't deassert, the sender doesn't deassert data ready until it sees this rising edge, okay? And then it can deassert data ready and get ready for the next transmission. Fully interlocked goes one more step in that. And once again, we place valid data, assert data ready. I accept the data. Data ready doesn't get deasserted, however, until it sees data accept. And then likewise, if I'm the receiver, I don't deassert data accept until I see data ready asserted. So it's fully interlocked. Data ready causes the rising edge in data accept, which causes the falling edge in data ready, which causes the falling edge in data accept. Now, I wanted you to examine this yourself on your own time to see the benefits here, but for your homework, one of the ways to consider what's going on is that noise happens, right? What happens if there's a random noise pulse? Let's say we've got data ready and there's some noise on the data ready line. Data ready line is low and there's a little bit of noise. I'm the receiver, what just happened? Everybody just went to sleep is what just happened. What just happened if data ready has a noise spike?
Data accept is going to go to high.
Yeah.
Most importantly, what does data ready looking like a pulse mean to me if I'm the receiver?
It means you should start receiving, like read in the data.
It means that there's valid data for me, right? So I'm going to go off on the data lines and grab whatever's there, which is nonsense, right? And I'm going to store it somewhere and maybe even advance a pointer in my buffer. So I'm now ready for the next thing, right? So what I just did was I assumed I got data, but the data was totally bogus and there was no real data for me to have. See how that would be a problem? So what does half interlocked do? Half interlocked basically says, you know what? You're going to keep data ready high until I assert data accept. So if I see what I think might be data ready, okay, I see this noise, I can wait and say, did this pulse go down or is it still up past a reasonable interval? If it's still up, then I know it's a real signal and now I can do what? Data accept. Okay. Up here, I can't do that because this is going to go low before it expects me to accept anyway. So I really can't distinguish a real pulse from a noise because in both cases, they will be low before I assert data accept. Here, it's waiting for me to assert data accept before it's going to take data ready low. So if I intentionally wait a certain amount of time after seeing data ready go high, then I can be certain that it's not a spurious noise pulse that caused the problem. Okay, you can analyze the same behavior here and say, well, what happens if other things happen, which I asked you to do in the homework assignment. Okay. All right. An extra bonus 20 minutes of class, or think of it as office hour if you like today, for no extra charge. Any other questions? Okay, see you all on Thursday, if not sooner. Good luck on the homework, and be sure to check in on D2L if you have any questions about the homework or anything else in class. All right, take care.
Thank you, Professor.
You're welcome.